In this video, we're going to take a look at linear inequalities. We've dealt with equations before, and we know equations are happening when I have a mathematical expression set equal to another mathematical expression. Well, inequalities are going to be such that we have a mathematical expression set less than, greater than, less than or equal to, or greater than or equal to another expression. So equations have the equality symbol. Inequalities have one of these four symbols. And again, this one is less than, this one is greater than, this one is less than or equal to, this one is greater than or equal to. We'll want to solve inequalities. And for the most part, we solve inequalities the same way as we solve equations. We'll simplify both sides of an inequality. We'll add or subtract numbers from both sides or to both sides. Then we'll divide by the coefficient of a variable. So for the most part, it works the same way as solving equations, except there's one thing I need to look out for. If I multiply both sides of an inequality by a negative number, or divide both sides by a negative number, then I have to flip the inequality direction. The reason for that is the following. If we have something like 5 is less than 8, 5 is clearly smaller than 8. If I were to multiply both sides by a negative, I would then be comparing -5 to -8. And on a number line, -5 is greater than -8 because -5 is to the right of -8 on a number line. The same thing is true if we have one positive number and one negative. The +2 is greater than or equal to the -3. If I multiply both sides by a negative, I get -2 versus +3. And it's clear that +3 is bigger than -2. So whenever I multiply or divide both sides by a negative, then I have to flip the inequality symbol. By the way, this just says multiply because whenever you divide, you can rewrite that as multiplying by the reciprocal. So let's do a couple of examples. Let's solve these two inequalities. In this first inequality, what I would do is I would add 9 to both sides. Both sides are as simplified as we can make them, so I'd add 9. Adding 9 to both sides of an equation will not change the inequality direction. So we still are going to have greater than. This says 2x minus 9 is greater than 15. When I add 9 to both sides, I'll have 2x is greater than 24. Then I would divide both sides by a 2. Now, dividing by a +2 does not change the direction of the sign. I'm going to write that step out just so we have it. But dividing by a positive number does not change the direction of a sign. So my answer is x is greater than 12. And that means any number that's bigger than 12 will make this statement true when I plug it in for x. So if I plugged in a 13 or a 473 or any other number bigger than 12, in fact, something like 12.01, would all make that equation true. In this second inequality, what I would do is I would start out by subtracting 14 from both sides. When I do that, subtracting a number from both sides does not flip the sign stays the same. And here's where it gets interesting. Normally, I would divide both sides by a -4, and that's what we're going to do here as well. We're going to divide both sides by a -4. However, because I'm dividing both sides by a negative, I have to flip the sign. And so what we'll get is a flip of our sign from greater than to less than. So we have to flip the sign since we divide both sides by a negative. And then we get the answer. We get x is less than -5. And what this is saying is that any number which is smaller than -5, when I plug it in to this equation, it will give me a true statement. So for instance, if I plugged in a -6, -4 times -6 is a +24, plus 14 gives me 38, which is in fact greater than 34. Or if I plugged in a -7, -7 is less than -5. So I'd get -4 times -7, that's a +28, plus 14, that's going to be 42, which is in fact greater than 34. So that's how we solve these inequalities. Notice that if we're using the standard techniques of solving equations, really the only time you're going to have to worry about flipping a sign is if in that last step where we divide by a coefficient. And if we're dividing by a positive coefficient, the sign stays the same. If we're dividing by a negative coefficient, then the sign flips. Now, our answers were algebraic inequalities in simplest form. We call the way I just wrote my answers the algebraic notation for the answer. However, there's other notations you can use to write your answers as well. So for instance, when we ended up with x was greater than 12, we'd have x greater than 12. That was the algebraic notation. We can write that in set notation by writing this way. It says all x values, this vertical line is indicating such that x is greater than 12. And then on a number line, we would have an open circle. Notice how we haven't filled it in. And then an arrow to the right. So a non-filled in circle tells us we cannot have equality. And then the arrow to the right says any number that's bigger than that will work. There's one other notation that we use a lot, and that's interval notation. In this case, if I said x is greater than a number, like x is greater than 12, I would say the solutions are all x values between 12 and all the way to the right on the number line. So from 12 to positive infinity. And that's the symbol for infinity here. Infinity is not a number, so it always gets a parentheses. Since x cannot be equal to a, or in my case it was 12, then we'd have a parentheses on that as well. When I don't have the equality symbol, I put a parentheses by the number. On the other hand, if I did have an equality symbol, let's say for argument, I have x less than or equal to b. The set notation would be all x such that x less than or equal to b. Since I have the equality on a number line, I'd fill in the circle. Again, this one would point left because I'm looking for values that are smaller than b. And then in the interval notation, I'd have a square bracket on the b. Once again, I'd have a parentheses, but this time on negative infinity. So let's solve a couple more inequalities and try to get the notation that we're looking for. We'll do some algebraic notation, some set notation, some number line notation, and some interval notation. If you want, go ahead and push pause on the video and try these two problems on your own. In a couple of seconds, I'll show you how these are done. So for this first equation, we'd start by simplifying the left-hand side. 5 needs to distribute into parentheses. When we do that, we get 5x minus 15 plus 2x is less than negative 17. Then what I would do is I'd combine like terms. 5x plus 2x is 7x. 7x minus 15 is less than negative 17. And then I would add 15 to both sides. 7x is less than negative 2. Now then I would divide both sides by a positive 7. Because I'm dividing by a positive number, the sign is going to stay the same. So sign stays the same since we're dividing by a positive number. Dividing by positive 7 would give me the algebraic answer that x is less than negative 2/7. So that's the algebraic answer. Let's in fact just write that out, that that's the algebraic answer. Now the set notation answer is going to have set brackets around it, and all it is set bracket x, then vertical line. That means the set of all x's such that, and then your algebraic notation. In this case, that's the set of all x's such that x is less than negative 2/7. Again, we call that the set notation. Now, as far as the number line goes, we're going to have to draw a number line. So that's what I've done. I've just created a really crude number line. And really, the only important numerical value is this negative 2/7. So I put negative 2/7. I mark that on the number line. And then I know that I want x values that are less than negative 2/7. So I want x values that are to the left of that. I do not want those x values to equal negative 2/7 because I don't have an equality symbol in my inequality. So I'm going to draw an open circle around negative 2/7, and I'm going to put an arrow to the left. Some people put thicker arrows, some people put thinner arrows, but this is what you would do. So that's the number line notation. And then lastly is the interval notation. Now, as far as the interval notation goes, I always go from left to right. The left-hand most value that I could plug in is theoretically negative infinity. Negative infinity is not an actual value, but you can think of the left-hand forever spot as being negative infinity. And then we would go up until we hit negative 2/7. So the interval notation would go negative infinity up to negative 2/7. Because infinity is not a real number and negative infinity is not a real number, we put a parentheses on it, on that side. Negative 2/7 has an open circle around it. I cannot plug in negative 2/7. So I put a parentheses around that as well. So that's the interval notation for this problem. Negative infinity up to negative 2/7, parentheses on both of those values. Let's go ahead and try the next one. I'm going to have to erase what I have on the number line, but we'll do the next one here. So for the next one, what I'd probably do is I would start out, since both sides are as simplified as I can make them, I would start out by subtracting 10y from both sides. If I did that, I'd get negative 2y minus 13 is greater than or equal to a positive 11. Then I would add 13 to both sides. That would give me negative 2y is greater than or equal to 24. Notice that when I added or subtracted from both sides, it did not change the sign direction. Now I'm going to have to divide by negative 2. And whenever I divide by a negative on both sides of the equation, I have to flip the sign. And that's because we're dividing by a negative. When I divide the left-hand side by negative 2, I get a y. I flip the sign from a greater than or equal to a less than or equal to. And then on the right-hand side, I get a negative 12. Now that is the algebraic notation. If I wanted to do a set notation, I'd do set brackets. In this case, my variable is y, so it'd be y values such that y is either less than or equal to negative 12. So that would be the set notation. As far as the number line goes, let me make that number line a little bit smaller. There we go, so it just fits. I would mark out where negative 12 was. Let's put negative 12 here. And then I do, instead of drawing a circle that's not filled in, since we can plug in the number negative 12, I'm going to fill in that circle. And so this is called a closed circle, one that I've filled in. The other circle is called an open circle. That's the one I don't fill in. So this is a solid circle since I can plug in a negative 12. And we're looking for values that are either less than or equal to negative 12. Less than or equal to, we're going to be pointing to the left. So that's my number line answer, or my number line notation. Now my interval notation once again starts out at negative infinity. it goes up to -12, but this time it's okay to plug in -12. That is, if I plugged it into my original equation, I'd get a true statement. So because I can plug it in and get a true statement, instead of putting a parentheses by the -12, we put a square bracket by the -12. And that's interval notation. Notice that when we have the equality symbol, then we have a closed circle and a square bracket on that number. When we don't have the equality symbol, we had an open circle and a parentheses on that number. And infinity and negative infinity always have a parentheses on those sides. Let's do a couple of other examples. Here we have 5x plus 8 is less than 5x minus 2, and 2x minus 9 is greater than or equal to 2x minus 14. You can try these on your own if you'd like. Push pause on the video, and I will show you how they are done in a couple of seconds. In this first one, 5x plus 8 less than 5x minus 2, I would start by subtracting 5x from both sides. That is not going to change the direction of the inequality. If I subtract 5x from the left, I just get an 8. If I subtract 5x from the right, I get a -2. Now, this says 8 is smaller than -2. That's always a false statement. I'll just put false instead of always false. And therefore, since this inequality is false, then this one is always going to be false no matter what value I plug in for x. Therefore, this is a situation where we have no solution. So we have no solution, or if you remember, we can also write that empty set symbol as well. So no solution or the empty set. By the way, this is the set notation. This is a shorthand for there is nothing in our set, basically. So that's the shorthand. The algebraic solution is no solution. I guess if you wanted to draw this on a number line, you could. You could just leave the number line blank. And in the interval notation, again, it would just be the empty set type of thing. So there's not a lot of different notations here with this example. In the second example, I would do a very similar thing. I would subtract 2x from both sides. Doing that gives me -9 is greater than or equal to -14. Now, that is a statement that's always true. I'll just write true next to that. And because that statement is always true, then the one above it always is true. No matter what I plug in for x, this statement is going to be true. Therefore, the solutions are all real numbers. Any number you plug in for x will satisfy and give you a true statement. The symbol, if you recall, for all real numbers is that capital R with double slash on the left-hand side. So even in inequalities, we can get inequalities which produce no solution or inequalities which produce all real numbers. Generally speaking, we don't graph those because the all real numbers is the entire number line. If you were to graph that, if somebody wanted to graph that on the number line, what you could do and what people would probably do is just put an arrow to the right and an arrow to the left, indicating that it goes on forever to the left and forever to the right. And if somebody wanted to do interval notation, they could do that as well. They would just go from negative infinity up to positive infinity with all real numbers. So forever to the left, forever to the right. Usually we don't, though. Usually we don't ask for interval notation or number line notation if we have all real numbers as our solution, or if our solution is no solution. Now, obviously, inequalities can get more and more complex. They can involve multiple steps. They can involve decimal values. So let's try a couple where we have more steps and one where we have decimal values. So one where you have a lot of steps, one where you have decimal values. If you want, go ahead and push pause on the video and try to solve each of these inequalities. In a couple of seconds, I will show you how these are done. The first step I would do is I would distribute this -5 into both terms. Now, we are multiplying by a -5, but we're not multiplying both sides by a -5. This is just a simplification step. So the direction of the sign stays the same, and we get -5x plus 10 plus 7 is less than 3x plus 10 minus 4x. Simplifying the left-hand side would give me -5x plus 17. And on the right-hand side, I would get -1x plus 10. I would subtract, or actually, let's do this. Let's add 1x to both sides first. When I do that, I'd get -4x plus 17 is less than 10. Then I'll subtract 17 from both sides, giving me -4x is less than 7. Now, when I divide by a -4, I'm going to have to flip the sign. And when I do that, I'll get x is greater than -7/4. Or if you wanted to rewrite that, that's -1.75. Also -1 3/4. However you'd like to rewrite that is perfectly fine for right now. The algebraic notation is exactly that. It's x is greater than -7/4, or if you'd rather use decimals, greater than -1.75. The set notation is the set of x's such that this algebraic property holds, x greater than -7/4. On a number line, I would simply draw the -7/4. Let's say it's right there. Since we do not have an equality, I make an open circle at -7/4. And since x needs to be bigger than -7/4, I'll point to the right. I didn't write down the number -7/4, but it's right there. And then with the interval notation, in this case, my lowest value is -7/4. My upper value is positive infinity. You can just write infinity. Infinity always has a parentheses with it. Since -7/4 cannot be touched, it's an open circle there. I have to write a parentheses on the -7/4 as well. So my interval notation is -7/4, comma, infinity with parentheses on both sides. So that's this first example. Again, no equality means open circle, means parentheses. For the second example, I don't have as much simplification going on, but I do have decimals, so I have to be careful about how I subtract. Here we're going to take and subtract 0.05z from both sides. Now, if I do that on the left-hand side, 0.6z minus 0.05 is 0.55 times z. Make sure you get the decimal place correct if we're dealing with decimals. 0.05 is not the same as 0.5. Then what I'm going to do is I'm going to subtract 0.03 from both sides. When I do that, I get 0.55z is less than or equal to 4.07. And then lastly, I would divide both sides by a 0.55. Now, the sign stays the same since we divide by a positive. So in this case, I would just divide by 0.55 on both sides. So we get z is less than or equal to 4.07 divided by 0.55 is a 7.4. And that's the algebraic notation. The algebraic notation is that z is less than or equal to 7.4. The set notation is very similar. It just says the set of all z values such that z is less than or equal to 7.4. On a number line, we'd mark 7.4 at some point on our number line, and then we'd make a closed circle. So fill that in. We're making a closed circle because we have the equality symbol. And since z is either less than or equal to 7.4, that means my arrow is going to point left. We can see the interval notation pretty clear once the number line is up. We're going from -infinity up to 7.4. Remember, infinity and -infinity always have parentheses on them. Numerical values are either going to have a parentheses or a closed bracket or a square bracket. In this case, we use a square bracket because we have the equality. Since we have the equality, we get a closed circle and a square bracket on that numerical value. So that's how we solve linear inequalities. Now, one more type of inequality expressions we have, one type of inequalities we have are ones that involve fractions. Remember how to deal with fractions. Hopefully you remember how to deal with fractions from when we solved equations in one variable. There's multiple ways of doing this. We could deal with the fractions if we wanted to, but what I'll do is I will use that multiplying by a common denominator to simplify my inequality before I go ahead and solve it. So let's do both of these. If you want to, you can push pause on the video and try both of these on your own. In a couple of seconds, I will show you how each is done. In this first equation, we have 5/3 times x minus 7/8 is greater than or equal to 1/2 times x plus 3. So we have denominators of 2, 8, and 3. Now, there's multiple common denominators we can use, but the smallest numerical value, smallest integer, positive integer value, which is evenly divided by 3, 8, and 2, is 24. So we're going to use the common denominator of 24. And that means I'm going to multiply both sides by 24, both sides of this inequality by 24. Now, because I'm multiplying by a positive, I don't have to flip the sign. The sign is going to stay the same. In fact, every time I multiply by a common denominator, I use a positive common denominator, and that'll help not having to flip the sign. So when we do 24 times 5/3 x, you get 40x. 24 times 7 over 8, or in other words, 24 times negative 7 over 8 is going to give me a minus 21. 24 times 1/2 x gives me 12x. And 24 times 3 gives me 72. And at this stage, I can solve just like any other inequality. I would subtract 12x from both sides. 40 minus 12 is going to be 28. So we get 28x minus 21 is greater than or equal to 72. And then we'd add 21 to both sides. We'd get 28x is greater than or equal to 93. Once I do that, then I'd take 93 and divide it by 28. I'd divide both sides by 28. Since we're dividing by a positive, the sign stays the same. And so we get x is greater than or equal to 93 over 28. Now, 93 over 28 is not a fraction that simplifies. So 93 over 28 is the most simplified version of that improper fraction. If you wanted to use an approximate decimal, you could. If you wanted to use a mixed number, you could do that as well. Now, the algebraic notation for that is just x is greater than or equal to 93 over 28. By the way, 93 over 28 as a decimal is about 3.32. The set notation is the set of all x values such that x is greater than or equal to 93 over 28. The interval notation Well, if you wanted to do the interval notation, you could do that right now. It's starting at 93 over 28. Since I have an equal symbol, I can use a closed bracket or a square bracket for 93 over 28. And then we're going to go up to positive infinity. On the number line, basically, we just have a 93 over 28, 93 over 28. And then I do a closed circle because of the equality. And then I'd have my arrow pointing, whoops, pointing to the right. So closed circle because of the inequality, arrow pointing to the right. There we go. So that's it. That's the solution in 4 different ways. That is 4 different ways to write that solution for this inequality. Now on the next inequality, what we would do, well, you can do this multiple ways, but before I get the common denominator, what I would do is I'd probably multiply that 4/5 inside the parentheses to begin with. That would give us negative 4/5 times z minus 4/5 is greater than 3 over 10. And then we'd multiply by a common denominator. Now the common denominator that I would use is the number 10 because 5, 5, and 10 all divide 10 nicely. So what I would do is I would take 10 and I'd multiply the left-hand side of this equation or inequality, not equation, but inequality. And then because I'm multiplying by a positive, I'll keep the sign the same and then multiply 10 times the right-hand side as well. Now 10 times negative 4/5 is a negative 8. So I'm going to end up with negative 8 times z minus 8 is greater than 3. 10 times 3/10 is 3. Adding 8 to both sides would give me negative 8z is greater than 11. Now at this stage, I did not have to flip anything up till now. But now I do have to flip the sign because we're dividing by a negative. So we have to flip the sign, and that would give me z is less than 11 over a negative 8. If I simplify that, that's negative 11/8. And you could write out the decimal version of that as well. But that's my final answer. The algebraic notation is just that. It's the z is less than negative 11 over 8, or again, another version of that number. The set notation is that it's the set of all z values such that the z value is less than negative 11 over 8. As far as the number line goes, we just mark negative 11 over 8. draw a circle around that. It's going to be an open circle. And then we want z values which are smaller, so we're going to point our arrow to the left. So open circle around negative 11 over 8, and then arrow to the left. Interval notation, therefore, would go from negative infinity up to negative 11 over 8, and we'd have parentheses around both sides or on both sides. So there you go. That's how we could solve these two linear inequalities. These ones obviously both involved numerical values which had fractions. And so we used multiplying by that common denominator on both sides as a tool of simplification. Now, another type of inequalities that we could see are what we call compound inequalities. There's a couple of types of compound inequalities that we could get. There's what I call the and type, and then there'll be an or type as well. And this is where two inequalities get put together in one line. A lot of times people will write a simple form like this. They'll say my variable x is in between a and b. So a is smaller than x is smaller than b. So that means any number between a and b would satisfy the inequality. It means x is greater than a, and also x is less than b. So both conditions have to be satisfied with this and compound inequality. There also may be or compound inequalities. And in the or case, we wouldn't be able to write it as a single line with two inequality symbols. We'd have to separate it with a statement like or. We would say something like x could be greater than some number, or x could be less than some number. And in this case, either condition could be satisfied for us to have a true statement. Let's do some examples. Here we have two compound inequalities. 9 less than or equal to 2x plus 5 is less than 24. And negative 2 less than negative x plus 7 is less than or equal to 18. You can push pause on the video if you want to try these on your own. Otherwise, I will do these in a couple of seconds. The key to solving a compound inequality like this is to realize that the left-hand side of this is one inequality and the right-hand side of this is one inequality. So if, for instance, I were to try to isolate the x in the middle, which is what I'm going to try to do, I want to subtract 5 from the middle. On the left-hand side, I would also have to subtract 5. But on the right-hand side, I would also need to subtract 5. In other words, if I do things to one side, then I have to do things to all three sides. Instead of dealing with two sides, I have three sides. So let's go ahead and do that. Let's subtract 5 from all three sides, the left side, the middle, and the right-hand side. If I do that, I'd get 4 less than or equal to 2x less than 19. And then I would divide all three sides by a 2. 4 divided by 2 would be 2. We do less than or equal to x, and then less than 19 divided by 2, which is 9.5, or 19 over 2, or 9.5. I think I'll use the decimal version here. By the way, notice that the signs stayed the same direction because I was dividing by a positive 2 on all three sides. The algebraic notation would be exactly that. 2 less than or equal to x less than 9.5. That means x can be anywhere between 2 and 9.5 and can be equal to 2 but not equal to 9.5. The set notation is exactly what you'd expect it to be. X such that 2 less than or equal to x less than 9.5. Now, the number line is a little bit different because in this case, we have two interesting numbers. We have a 2 and a 9.5. So we're going to mark out where the 2 is. We're going to mark out where the 9.5 is. And we know that the x values can be anywhere between 2 and 9.5. They can be equal to 2, so we're going to put a closed circle on the 2, fill that in. But they cannot be equal to 9.5, so we're going to put an open circle on the 9.5 and not fill that in. Then we connect the 2 because x can be anywhere in the middle. X can be anywhere between this 2 and this 9.5. And so that's the interval, that's the number line notation. Now let's go ahead and do the interval notation. We can see that the lowest value in the interval notation is 2. The highest acceptable value goes up to 9.5. Since I have an open circle at 9.5, I'm going to put a parentheses on that side. Since I have a closed circle at 2, I put a square bracket at the 2, or a closed bracket at the 2. So this is how you would do a compound inequality, one where we have sort of three sides to it, which is the and type. X has to be bigger than 2 and X has to be smaller than 9.5. Let me erase that number line and move on to do the next problem. The next problem is very similar. We need to isolate X in the middle. In this case, I would subtract 7 from all three sides. Subtracting 7 does not change the direction of anything, any of the signs, excuse me. And then I divide by -1. Now, when I divide by -1, -9 divided by -1 is a 9. I would have to flip this sign. So X is smaller than 9. 9 is greater than X. And then I'd have to flip the other sign as well. So when I divide all three sides by -1, I have to flip both inequality symbols. Now be careful here. Technically, -11 is the smallest number and 9 is the biggest number. So you could, using algebra, write it this way. Or if somebody wanted you to, you could write this as -11 less than or equal to X less than 9. Notice what I did. I just put the smaller number on the left, and then I made sure that the inequality symbol matched up. Here it was x is the bigger or equal to negative 11. This is x is greater than or equal to negative 11. Same thing as saying negative 11 is smaller than or equal to x. You don't have to do that, but I like doing that, especially when I write things on the number line and in interval notation. I think it makes a lot of sense to go smallest on the left, biggest number on the right when I write it on the number line. My set notation is going to be the set of all x's such that x is between negative 11 and positive 9. My number line will have negative 11 on one side, positive 9 on the other. 9 cannot be touched because it doesn't have an equal sign. 11 can be touched, so we fill in the circle for 11, but we do not fill in the circle for 9. Excuse me, negative 11. Fill in the circle for negative 11, but not for positive 9. And then it's all values in between there that make that a true statement. The interval notation would go square bracket, negative 11, comma, 9, parentheses. Can't touch 9, can't plug in 9 to get a true statement, but we can plug in negative 11. By the way, sometimes people think they're going to use square brackets on everything, and so they'll put like, oh, we can't touch 9, so the next smallest number is 8. They'll say that, but they'll be wrong because there's a lot of numbers between 8 and 9. 8.5 is between 8 and 9, and 8.99 is between 8 and 9, and 8.9999 is between 8 and 9. So we can get all the way as close to 9 as we want, but we just can't get to 9 exactly. So that's why we have the distinction there. Now let's take a look at the or compound inequalities. This says 2x minus 1 is greater than 10, or 5x plus 1 is less than negative 3. Then the other one says negative x plus 7 greater than or equal to 18, or 3x minus 9 is greater than 12. If you'd like to try these on your own, go ahead and try these on your own. Push pause on the video, and in a couple of seconds, I will show you how these are done. On these or type compound inequalities, what we could do is we're going to solve each one individually. Now, I'm going to kind of do them at the same time, but you can do these individually. You can do solve one and then solve the other if you'd like. In this first one, the left-hand side inequality, I'd add 1 to both sides. That would give me 2x is greater than 11. Again, I'm going to solve both at the same time. So 2x greater than 11 on that one. And then on the other one, we have 5x. I'd subtract 1 in this. 5x is less than negative 4. Some people would have just finished this one off and divided both sides by 2. If we did that, we'd get x is less than 5.5. Or in this one on the other side, x is, oh, I'm sorry, my bad. I wrote the wrong symbol, excuse me. X is greater than 5.5. When I divide both sides by 2, I'm dividing by a positive, so I do not have to flip the sign. On the other one, when we take -4 and divide it by 5, we get x is less than -0.8. And that's the algebraic notation. The algebraic notation is either x could be greater than 5.5 or x could be less than -0.8. The set notation would say the same thing. The set notation would say the set of all x's such that x is greater than 5.5 or x is less than -0.8. Now, I want you to understand what's happening on this number line. I'll make it a little bit bigger than I usually do. We're going to have a 5.5, and we're saying x could be bigger than that. So I draw an open circle and an arrow pointing to the right. Or x could be smaller than -0.8. Again, I'm going to draw an open circle there, but I'm going to put an arrow to the left. So there's kind of two regions that will work. The -infinity up to -0.8 will work. And then the 5.5 up to +infinity will work. The way you do that in interval notation is you just write both intervals. So you write -infinity up to -0.8. And then the other interval, if you're doing this right now on your own, make a space in there because I'm going to add a symbol between the intervals. 5.5 up to +infinity. Now, the symbol that we use to indicate either of these notations will work, or either of these intervals will work, is called a union symbol. It looks like a cup, essentially a big U. And that's saying either this one is fine. If our answer is in here, in this region, we're fine. And also, if our answer were to be in this region, we'd be fine. That's what this union symbolizes. Again, that's the union of these two sections. So there you go. Compound inequalities with OR, we just end up with two regions. Most of the time they don't overlap. And then we put them together utilizing a union symbol. Let's look at the next one. In fact, let me start this next one on a new page so I have plenty of room. Now, this first equation, I would have to subtract 7 from both sides. That would give me -x greater than or equal to 11. Then I would have to divide both sides by a -1. That would flip my sign to say x is greater than or equal to -11. So that's the left-hand inequality. On the right-hand inequality, I would add 9 to both sides. That would give me 3x is greater than 21. Oh, I did that again, didn't I? I'm sorry. I said I needed to flip the inequality symbol there, and I did not flip it. This is what happens when I get going too fast. So, my apologies. When I divide both sides by a negative, we have to flip from greater than or equal to less than or equal to. Here I divide by a positive 3, so I don't have to worry about flipping the sign. So I get x is greater than 7 or x is less than or equal to negative 11. That's the algebraic notation, x less than or equal to negative 11 or x greater than 7. The set notation is just the set of all x's such that that happens. For the number line, less than or equal to negative 11, we'd write a negative 11. Since we could have the equality here, I do a filled in circle or a closed circle, and then I point to the left. We'll write 7 here. Because I don't have the equality, I put an open circle at 7, and then numbers have to be greater than 7. So either of these two regions will satisfy this equation or this equation, or this inequality or this inequality. In terms of the interval notation, we're going to go from negative infinity up to negative 11 with a square bracket at negative 11, and then union that with the interval from 7 to positive infinity. And so those two intervals combined give me my solution to this compound inequality. Hopefully that all makes sense. We have two regions which work, and so we're combining those with a union symbol. Union is just a fancy way to say either if it's in this one, it'll work, or if it's in this one, it'll work too. Now, there's lots of other types of equations that can deal with inequalities. We can take any equation that we deal with in this course and turn it into an inequality. So if we had an x squared, or if we had an absolute value, or if we had an exponential equation, then we could turn that into an inequality by replacing the equal sign with a less than, a greater than, a less than or equal to, or a greater than or equal to. Obviously, in this section, we are only focusing on linear equations and linear inequalities, but we could expand this to other things as well. And in fact, we'll see expanding this to other things once we get into those sections.